Greg. I come from dunnhumby, and I'm a research data scientist working on retail data. I've been at dunnhumby for around 2.5 years now, and I come from an academia background, mostly doing PhD in theoretical physics. So, as you can see, today I'm going to be discussing global and local information that arises at different scales within graph networks, analyzing using analysis via graph neural networks, specifically within retail graphs. So before I actually jump into my research, I'd like to tell you the company where I do my research at, and that's dunnhumby. And at dunnhumby, we actually believe in creating a better world by putting customers at the heart of decision making. We are actually a global leader in customer data science, and we help retailers and brands grow by understanding and serving their customers better. And the way we do that is we combine data, advanced analytics, AI with retail expertise to enable smarter and faster decision making. We specialize in category management optimization, customer loyalty enhancement, and maximizing owned media impact. We also have decades of experience with leading retailers and brands worldwide. We transform complex customer data into actionable insights for sustainable and customer-first growth. So globally, we have a massive client network spanning Asia, EMEA, as well as the Americas. We actually serve more than 56 retail clients and also partner with 1,250 plus CPGs. We're actively engaging 1 billion active customers across 30 billion baskets of daily transactional data. And we're constantly trying to evolve to help clients make decisions that encourage customer loyalty. So I'm going to be discussing exactly part of that innovation. So, before we actually jump into the talk itself, let's set the scene. So, graph neural networks, some of you might have already heard of them, they aren't actually very new. It's not 2005, it's not even the 2010s anymore, sadly, it's the 2020s. So, graph neural networks, or as I'll refer to them, GNNs, have actually been in the industry for quite a long time and have been used relatively successfully. So they've been used by quite large companies, giants in the industry, such as Amazon, who have been using it in AWS, or Pinterest, who have their proprietary algorithm called PinSage, and also other companies like Uber or X, previously known as Twitter. So then, what is it actually that we're trying to aim for? Since graph neural networks are already kind of relatively widespread. Well, what we want to do is actually improve how they're being used, how we can make all of them better, essentially. And that is exactly what we're going to be focusing on in this talk in its entirety. But let's see our approach. Well, first things first, I'm going to give you a brief introduction into graphs and GNNs, since I'm aware that maybe not all of you have been exposed to them before. And I want to explain their properties from a non-technical standpoint. So what you'll notice is this talk is actually going to be somewhat non-technical to kind of introduce everyone to the idea of graphs and how we can make them better so we can all understand it more. Now, the second part of the talk is going to be focusing on, so this is the most important part, the interaction between data and structure. So you'll see these two words popping up a lot. I'll make sure to always point it out. So we can actually use it to make better predictions within GNNs. And then lastly, I'm actually going to walk you through a few examples of global and local graph features, which you might not yet understand, but I hope by the end of this talk, it'll become much clearer. Okay, so let's jump into it. First topic of conversation, what are graphs? Well, as good data scientists, we should always start at the very beginning of the pipeline, right? With our data. So well, most of us are actually exposed to what is known as tabular data. And just in case you haven't heard that specific phrase before, it's just data that is contained within a table, basically anything. And me specifically, I'm a retail data scientist. So I work with transactional data. And as you can see, oh, I forgot to turn on my pointer here. Okay, so as you can see here, this is what transactional data looks like. So this is just some dummy data I cooked up for this presentation. You can see that each one of the rows actually represents a purchase that a customer has bought a specific product at a specific date. And then, just like with any other tabular data, you can record more features, which might be, for example, here coming from the time of the purchase. In this case, I included the quantity bought and potentially the money spent. So what I want to do is, instead of looking at the standard data in your regular way of analyzing row by row in kind of like an isolated fashion, I want to start identifying relationships. So let's imagine that we have these two entities, the customer interacting with the product, and we identify this as a relationship. And once we start connecting all of these things and building a much more global picture, you see that all of these interactions actually start building something new. And this is what we refer to as graph networks, or more colloquially, I will call graphs. And this shift is kind of subtle, but it is very powerful. As we will see that later on, we'll actually make heavy use of this specific way of looking at the data to infer more information from the structure that it creates. So now we have actually identified what graphs themselves are. Let's define them a little bit more rigorously. So as you saw, graphs represent a more global view of the data itself. They capture all relationships at once. But the actual idea of graphs, so the graphs themselves they aren't the data, they just represent data, the relationships between them. And they're not actually as alien as you might think. You're actually kind of exposed to it daily without really thinking about it. They can represent a lot of lots of types of data without even you realizing them. So for example, the most obvious ones would be networks, hence the word graph networks. So social networks would be one example, which can be really well represented by graphs. Whenever you interact with other people on a social network, you friend them, you like their posts, you send messages between each other. All of these are types of interactions and then can be used to build graphs. Now, natural language and images can still be represented by graph data, but it might not be as straightforward. So they might not lend themselves as obviously, but in natural language, you might have relationships between words within a sentence, and in images, you might have relationships between the pixels. So they can still be represented as graphs, but you might not choose to do so. And then the last example was the retail data I brought up, which is something that we'll be focusing on a little bit more over the course of this talk. Now, I'd like to point out before giving the definition is that shifting your perspective to a more graphical view doesn't actually introduce any new information. It's just a matter of perspective. So you're not actually bringing in new information. It's still the same data, but you're just choosing to look at it in a different view. So how do you actually build a graph? Well, since they represent relationships, the best thing to do is to actually identify what the relationships are between. And these can be any types of objects. And more rigorously, we call these nodes. So this could be, for example, customers, products, credit cards, stores, anything that you can think of that could have relationships. And then the relationships themselves are represented by the edges. And I thought that in order to consolidate all this information, now that we kind of understand how graphs are defined, is to give you some examples. And I've decided to bring two specific examples from different parts of the graph spectrum, so to speak, which I think convey how graphs can behave in a very nice way. So the first example is a very large graph, and this is actually coming from a study that was done by university students a few years ago. And some of you might recognize this because this is actually data that was taken from HBO's hit series called Game of Thrones. And just in case you're not aware of it, don't worry, I'm not going to be spoiling anything about that show. And also, it was a famous show that stopped airing a few years back. But the important thing about it is that it contained a lot of characters, notoriously a lot of characters. And these characters in the graph are represented by nodes, and their interactions are represented by edges. And the interaction strength, or the times they interacted, it reflects how thick these specific edges are. So the reason I brought this up as a nice example is because it shows you the extent of this graph information and how well it kind of shows the interactions. While obviously you could look at this through tabular data and you'd see a bunch of rows displaying the interactions. But here you can already start to kind of infer some surface level details. So for example, you can tell maybe which characters are important to the plot because you can see that they are a center of a lot of interactions. Whilst you can also start to see maybe certain cliques or factions emerging just by virtue of looking at the graph in this, looking at the data in this graphical sense. And now let's go to the other example, which is actually the polar opposite. So this was a study done by Google. Actually, I can recommend the actual website. It's really nice. They have a really nice interactive explanation if anyone wants to see it later on. But basically, what they did is they did a study where they tried to predict the whether a specific molecule a specific organic molecule was pungent or not pungent just based on its graph structure, where the nodes themselves represented atoms and the edges between them represented the bonds. And the reason why I think this is a really nice contrast to our previous example is because you see how little and how small graphs can get. And as it turns out, the study actually predicts for these individual graphs. So this is actually a bunch of disconnected graphs which have labels that you're predicting for. So as you can see, even the problems that you're solving are very different, because for the previous graph, you had one big connected graph that you might be predicting for the aspects of the graph. So let me just give you a quick summary. So far, we've seen exactly where graphs and graphical structure might come out of, and this and how relationships arise and how structure kind of comes from graphs. But the next thing that we're going to look at is how we can prepare the data using graphs, and then how this data will actually be ingested by models themselves, which we haven't actually yet talked about. So hinting at graph neural networks. But some of you might have already started asking the question that this is all well and good, and you've talked about structure, right? Whenever you build graphs out of data, first you have to build, well, you have to build the graph itself, you get the relationships. But where does the data actually come in? What is it that a specific model that I would, let's say, apply to this, where does it get the information for the predictions? And that's exactly what I want to talk about. Because when you actually build a graph, inherently, there is a natural hierarchy that appears. So this is not something that is imposed. It is kind of hard-coded within the graph. It's by virtue of you constructing the graph itself. So what do I actually mean by this hierarchy? What is this hierarchy between? Well, it's between what I call, or I refer to as graph objects. So these graph objects are just a fancy way of calling elements of a graph. And some of these elements you will have already encountered. So some of the most basic ones will be the nodes and the edges. But what I haven't told you yet is these are actually, they can function individually as data containers. So what do I mean by this? I mean that you can start attaching bits of information to these specific entities within the graph. So as an example, to the nodes, you can attach, for example, attach what type of node it is. So in our previous retail example, you might be talking about customer nodes or product nodes or store nodes, etc. And at an edge level, you might be talking about what features or data you might be attaching to interactions. So again, just back to our previous example, you might be talking about quantity board or the direction of the interaction, or maybe the price that was paid, etc. And as you go higher in the hierarchy, you start to get a little bit more abstract. And this is what we call subgraphs. So these would be parts of the whole graph, such as in a retail setting, you might have customers who form a graph that have similar purchases. And you can attach data into this specific subgraph as well. And you can then go to the very top level and start maybe attaching data there, which is attaching data to the whole graph. So what you might have here is, for example, geographic information of where this specific market is located, or maybe how many total customers there are in the graph, or how much is the total spend or the total stock of the specific store, or the interactions that you're talking about. So some of you might already be thinking in a database sense, and this is actually very close to the description of what a graph database is. So graphs are really good at that, actually, to access the data in very kind of efficient and nice ways in a structural fashion. But this is not, in my opinion, the biggest merit of graphs, because again, just to bring out this theme that I will continuously bring out, is the interplay between data and structure. And the data is there, but then the structure is also something that we have to consider. So what graphs are really good at is actually breadcrumbing information. And that's also why I wanted to bring up this nice generated image, which is a tale of Hansel and Gretel, if some of you are familiar with it, where the graph itself will be laying the crumbs of the information, and the model that we will be using is picking up that information in a coherent way. So what I'm trying to say here is the graph contains the information, but also tells the information what routes it's allowed to propagate in. So that's these structural bits where you can follow the flow of information. And that's very important. So now let's actually move on to discussing what type of model can naturally or natively take that flow of information. And that is where GNNs come in. So GNNs themselves have been a huge area of research. So there's probably hundreds, if not thousands, of papers out there about different GNN architectures, and there'll be way too much to actually discuss. So just like I promised before, I actually want to focus on a more top-level view of GNNs and not discuss any specific architectures. So, but there are some features which GNNs share across the board, which I feel like is already going to give us a really good understanding of how they work in a nutshell, basically. And one of the specific powers of GNNs is message passing. So, how does message passing work? Well, GNNs themselves, just like any type of neural network, aim to learn representations of objects. So what this means in a simpler language is we're basically trying to uh, take information and compactifying it in a way which is learned, and then output some compact bunched up information, which is very useful for predicting aspects of that specific object. And that's exactly what GNNs do, except with graph objects. So in this example, we can look at a specific target node. Like imagine we're trying to predict the representation of this specific target node. And the way this would be happening is we consider the neighboring nodes of this specific node. So as you can see, these are all nodes that are connected via edges. And then what the message passing does, and this is why I really like the name, because I think it's really aptly named, is all the nodes pass their information, which is contained within their container, which can be features, it could be some embeddings that the nodes might contain, and then they pass it to the target node where the neural network actually processes that information. So it filters it, it weighs it, and then aggregates this information in an architecture specific way. But for us, it's enough to know that it aggregates this information and then outputs this fresh representation for the node, which can then be used in a downstream task to predict whatever we're trying to do. And again, there's no reason to only do this once, right? The graph itself can be quite extensive. So what you can actually do is do this process repeatedly. So what you can do is start very far away and start to recursively pass messages between the nodes until you reach a specific target node of interest. And what this basically does is it aggregates information from relatively far away within the graph network itself. And this is effectively how representations are generated within most graph neural networks. So why is this actually useful to us? Well, again, remember that description between the data and the structure. The GNNs actually learn structure-aware representations because remember that message passing can only occur between nodes that are connected. So it must respect the flow of the data, which means that any representation that you learn will learn it in such a way that it actually understands the structure of the network. And then let's move on to actually how we use these specific representations. So this is the point where I think it will become really easy to identify how graph neural networks can actually be used to solve everyday tasks that most of you are probably already used to from your machine learning careers. So here, we just have to reframe it a little bit in terms of our graph language that I just introduced. So here on the left side, we have our usual problems in machine learning, the classification, regression, unsupervised learning. And then on the top here, we have our graph objects. So for example, if we wanted to learn representations of nodes and then use them to classify, well, the nodes themselves, in a retail setting, this could be equivalent to doing customer segmentation. So we could be predicting specific segments for customer nodes, or we could be, for example, predicting specific product attributes that are categorized. So this would be, again, another type of node classification. We could also do edge regression, for example. And just to tie this again to another example, this would be equivalent to predicting basket size per customer visit, for example, or maybe predicting customer spend for a specific visit. Or we could also do graph level, maybe unsupervised learning. So you can look at an entire graph of interactions and maybe try to classify, but maybe you try to identify whether the sales patterns are unusual. Maybe they're fraudulent or there is some sort of anomaly. So as you can see, there is you can really easily go back from this area of graph neural networks to your kind of well-treaded usual machine learning tasks. And what I want to now move on to talking about is how we can use all the information that we've developed so far in this talk and kind of move past what we've already been using. So as I said before, graph neural networks have existed for a while, And there is a lot of them. So we could spend ages talking about the individual architectures, which, don't get me wrong, all of them have their own merits, and they all have their downfalls. We could discuss about different applications. We can discuss different implementations within PyTorch or TensorFlow. But what I want to actually focus on is something that underlies all of graph neural networks. Well, the actual data itself, the graphs. Because the more you understand the graphs, the more you will actually make better predictions and make the graph neural networks actually absorb more data. So this actually single-handedly should improve all graph neural network models if we manage to give them basically better data. So how do we do this? Well, this is by actually going back to the very first bit and understanding where information comes from the graph itself. So I was maybe a little bit deliberately, but vague in what kind of features we actually pass into the graph neural network. And if you think back to a few slides ago in a few previous sections, I talked about graphs themselves being data containers. But that is, as it turns out, will be somewhat of a superficial way to actually take information from graphs. There's actually a set of information that comes from just virtue of the graph being a graph and containing that structure. And that is where what I call extrinsic and intrinsic features arise. And that is exactly what I want to discuss and see how this will actually lead back to the interplay between data and structure. So let's dive into it. What exactly are extrinsic features? Well, just like the name suggests, they are actually external to the graph structure itself, whilst the intrinsic features come from within the graph topology. All right, in more simple terms, extrinsic features are attached to nodes or edges or whatever graph objects. So this again comes back to the containers that we've looked at before. So the way I like to kind of imagine this is imagine you have the graph kind of hovering in empty space, maybe as some sort of a 3D model. And on top of it, you have some aspects, some metadata kind of floating on top of the graph, right? So it's not directly attached to it. It's just kind of an aspect of it, if you will. And intrinsic features themselves emerge directly via the structure. So when you build the graph from the relationships, that intrinsic feature is already within the graph itself. So you don't have to actually bring it in from the outside. It's just already there because you chose to represent the data as a graph. And for this reason, extrinsic features, because they're not actually attached to the graph, they are independent of connectivity. So what does this actually mean? This means that, just to go back to your retail example, if I were to pick a customer node and a product node, right? The customer will have some extrinsic features such as their name, where they live potentially, like a geographical location, and some other stuff, whatever age, demographic, so on. And the product will have, again, similar information, some category, product information, description, picture, etc., whatever. And the connectivity, the structure between them will be reflecting how many times the customer has bought the product or how it interacted with the product. Now, just because you buy the product more times, that extrinsic information isn't going to change, right? Just because you buy the product more times, your name isn't going to change, or you're not going to move cities because of that, at least. And same with the product, right? The product type isn't going to change. Whilst intrinsic features, they're much deeper than that. Imagine them as kind of really low level, low level features, which summarize effectively the position and the roles of individual graph objects. For example, nodes and where they're located, and these kind of really deep structural informations. So again, by virtue of this independentness, extrinsic features are easily updated and modified, right? So what I mean by this is, for example, if you're in a web shop and you want to change your username or some information that you have, you can very easily do so. And just because you change your username, that doesn't mean that your underlying purchase history has changed, right? But intrinsic features, however, are a little bit more stable and harder to alter because of this deep kind of low-level aspect of them. So if you actually change the intrinsic features, you're effectively changing the structure of your graph. So again, remember that because GNNs interact with graphs via message passing, this will fundamentally change the flow of information. So you're actually absorbing data in a fundamentally different way. So how does this actually, okay, so what am I trying to say with these two things? Well, okay. So I want to come back to the interplay between data and structure here. Imagine again that you're building a graph from first principles. You have your data, and then you build the graph using the relationships. Now, if I just, it's like a skeleton. So you have basically a skeleton of your data. If I just gave you this specific graph, let's say to another person who's not aware of the data, they would not be able to tell you what problem you're trying to solve, right? Who knows what that graph is representing? It could be molecule, it could be a group of customers interacting with products. You would never know, right? Now that's exactly the interplay between extrinsic and intrinsic features. Extrinsic features is are the ones that add contextual signals to the GNNs. So once you start attaching all of this data, it contextualizes the problem for the GNNs, and now the GNNs can more efficiently learn exactly what it is that they're trying to predict for. So now you can start to see this vicious cycle forming between extrinsic and intrinsic features, where the intrinsic features are actually the ones that are guiding the learning. They are showing where the information should be flowing. So then what actually happens in the GNN is the message passing. The messages themselves will be containing this specific superficial information, and then the intrinsic structural information will tell that information how that information should be processed within the GNN. Now, let me just reveal that these features are exactly the graph-based features that I've been talking about before. These are the features that we want to be concentrating on. Why? Is because, as it turns out, while both of these exist, in data science, we've been really heavily leaning on this side of the features, right? This is just regular data, regular features that you can absorb from anywhere, right? I can go out, record more data from the stores, and then I can just bring more extrinsic features. Or again, I can just hire data scientists to perform more feature engineering. And sure, while that's going to give more insight, obviously bring in some more data expertise, they're still somewhat superficial because here we don't have that much of this. And again, improving these intrinsic features, right, or bringing more of them, in turn improves how well these features are actually absorbed. Right. So with that, let's actually talk about a really good simple example of an intrinsic feature or an intrinsic graph-based feature, as I like to call them. And the first one, well, the first and only one that I'm going to be talking about is centrality. So what exactly is centrality? Well, in reality, centrality is quite an easy concept to grasp. It's actually just reflecting how popular a specific node is. So in a retail setting, you would have a customer node which interacts with a lot of product nodes, and its centrality will essentially tell you how many products it has interacted with. So you can see that it is very simple. You might be asking, well, I mean, this is really basic information. Why would this be useful for us? Well, first of all, it's clearly intrinsic bit of information because if you change this number, you're fundamentally, again, changing the flow of information, right? Because if you interact with a different number of products, then you are suddenly passing information very differently within your GNNs. So while you can already use the number itself, so for example, if a centrality is a specific number, you can encode that information and then pass it straight to the GNN to be used. And that is already one way of using it. I feel like that is a very superficial way of using it because it's not actually making use of the actual graph itself. So instead, what you could be doing is constructing your graph in such a way that it absorbs the information relating to centrality. And that is exactly what I want to talk about on this slide. Because as it turns out, there is not just one way to look at centrality. There's many different types of centrality, which in turn will tell you how information is propagating within the graph. So potentially the most basic one that whenever you construct a graph without any major changes you will encounter is called non-unique centrality. So back to our retail setting, let's assume that I'm going to store on a weekly basis and I buy, I like to buy milk, among other things, obviously. I just really like milk. And I buy it on a weekly basis. Now, if you look back 6 months from now, what you will see is a lot of repeated purchases of milk and potentially other products. But what I'm doing is each one of the purchases actually has its own edge. Now, as you can see, when you do message passing within your graph for the graph neural network to learn, all of these repeated edges will be used as avenues for information propagation. So now what happens within the graph neural network, it starts to pick up on habitual purchases. It will start to predict, it will start to pick up on, it will start to weight the predictions heavier towards products that that the customer might be more heavily purchasing because of this specific habituality. And instead, you might do, well, in the next example, what if you want to capture a different set of information, you might do the complete opposite. You might just want to do unique centrality. So here you construct the graph in such a way that each one of the purchases is only recorded once, or rather you only give it one edge. So let me give you an example. So let's say that, again, I go to the store and I buy, again, milk multiple times, or product multiple times, because these are groceries. I tend to purchase them repeatedly. But I only record new edges when a new product actually is purchased. Other products, you can record repeated purchases to potentially extrinsic informations by potentially putting that number of how many times it was purchased in a container rather than actually changing the intrinsic graph information, right? So this is what unique centrality will do for you. Instead of learning potentially habitual purchases, what you will learn about through message passing is the breadth of the customer, potentially how varied my purchases are across the board. And you can do other things. You can look at in versus out centrality. So here, it is easier to potentially explain it through social media or message sending, where you potentially want to record the direction of the actual information flow. So here, maybe the number of incoming messages versus number of outgoing messages is very different. Like, imagine that I'm a very popular person. Oh yeah, that sounds like I'm bragging, but I'm really not that popular. But but maybe I would be receiving a lot of messages versus sending out only a few. So in this case, you can see that the propagation of the incoming information will be very different compared to the outgoing one. So again, the graph neural network will learn something very different. And the last one that I want to talk about is maybe when you can start to zoom out a little bit. So in a retail setting, maybe just naturally creating the graph, you will see a lot of erratic purchases. You will not be able to make sense because again, customers buy a lot of things. But then what maybe you can start to look at is the customer's interactions with individual categories rather than the individual purchases themselves. And then you might start to see that this customer actually might have a lot of varied purchases, but only within a specific category. So now the propagation of information, if you just use the nodes of the categories themselves, might be much more simplified and easier for the graph neural network to pick up via message passing. And that's exactly why they're useful. And again, so these are all local ways to extract structural information from the graph neural network, sorry, from the graphs to then feed into the graph neural network. But there's no reason to use these in isolation. You would use them together. And again, this is just one type of intrinsic information that you can have in a graph. We're barely scratching the surface of what you can actually put into graphs, right? But again, like I said, this is only the local level information, right? Intricacies, as it turns out, exist within graphs at every single scale. So you might, your graph might be holding a lot of relevant information at a node level, node edge level within neighborhoods, or you can even have graphs that contain a lot of good structural information at a global scale. Why might you do that? Because local patterns, just like in purchases, can look very similar. So what you might want to do is look at broader structures to identify their specific contexts. So potentially zooming out can actually simplify the problem sometimes. And this actually brings in some really nice examples. So for how GNNs can learn more global structure-aware representations through message passing. And I actually simulated these two specific examples. So this is actually simulations that I've run myself here, where I constructed two separate graphs in two separate kind of scenarios of information. And I want to tell you exactly how this global information is captured in an intrinsic way. So here on this side, so it's basically a GIF, but the simulation starts when each one of these nodes are actually colored the same way. So the color actually represents a representation, a node embedding, which reflects the information captured within the node. So they all start with the same information. And then what I do is I pick this specific node and I perturb it. I give it an overwhelming amount of new information, and then what happens is through message passing, the information actually flows down the graph. And as you can see, the intensity of the change is captured within the kind of outgoing neighborhoods. So obviously the ones that are closest will be the most severely affected, while as you go down the graph, they're going to be less and less heavily affected. But this kind of already gives you, while it's certainly somewhat obvious, but it does give your graph and your graph neural network through message passing an understanding of the global structure of the graph itself. And remember, I have not brought any kind of extrinsic information here. All the information I'm dealing with here is only by the virtue of how the graph itself is connected, right? Because the moment I change any of these connections, the information propagation is fundamentally altered, right? So now the second example is a little bit of a different setup. Now, what I chose to do instead is where the simulation begins, all of the nodes are actually differently colored. So that means that we're assuming that each of them contain different information. So they're randomly structured initially, and then through the act of message passing, so just aggregating and passing message in such a way that the GNN explores the graph, it starts to cluster the nodes in a way where it has learned structure sensitive information. So as you can see, effectively it ends up in three structures where it has identified that, oh, these are somewhat unique points within the graph, globally speaking. So as you can see here and here, these are the kind of nodes where the graph or the GNN is aware that these are at the edges, so they are in somewhat of a unique position. And then the very final node here in the middle is also in a unique position that you can't really compare to the other nodes because it's in the middle and it has very different interactions compared to the rest of the nodes. So as you can see, this is again intrinsic information that kind of captures global roles of the nodes themselves. And again, I have not brought in any extrinsic information. You have no idea what I could be possibly using this graph for, right? It could be potentially a molecule or anything else. But then I like to relate this back to the interplay between data and structure. So imagine that now I suddenly bring context into this, potentially retail data, and now I start to put customer labels and all of this information on top of these nodes, and then combine it with the structural information, and then potentially bringing new structural insights coming from graph-based features. And then, because of this interplay between the data and the structure, you start to see more clearly uh, and make better, potentially more accurate structure-aware representations. And that actually perfectly brings me to the conclusion of my talk and where we're actually heading and what I anticipate we'll be doing next and what I also personally want the area to go towards. So first of all, let me just recap exactly what we've seen. So we've looked at graphs from the ground up in a nutshell, and we've looked at how information is potentially contained within graphs and how GNNs extract that information, right? But then we also discovered that graphs are actually somewhat unexplored gold mines of information, right? While we can always add more extrinsic information, just pile on top more and more data, and that, if it's insightful data, will of course work. It has worked, right? But there's actually so much unexplored local features, such as which reveal fine-grained patterns, such as what we looked at centrality. But again, that's only scratching the surface. There's much more than that. And also global features, which in turn try to capture a much more broader sense of what the nodes themselves might be, or specific clusters, or the way they're connected globally. So what I see happening and where I'm also pushing with my research is to see an evolution of graph feature engineering. So we want to go beyond what we can do with GNNs right now, instead of just using them kind of out of the box and then putting more and more information into them, but actually add more graph native features. And then see these new graph native features combined with the extrinsic graph features to guide better representation learning. So as you can see, in this new frontier, the opportunity isn't just using graphs. We've been doing that for a while, and we've been doing that quite well. It's now how we can improve most of them, how we can extract more information in order to get more domain-informed graph features that can also generalize better. Again, since graph-based features, as it turns out, are not tied down to specific problems, they actually generalize quite well, so that you can actually turn this information into more insightful structure and more structurally aware generalized representations for graphs. Thank you very much.
Amazing. Round of applause, please. Let's see some emojis. Come on, let's see the emojis. Let's see some comments in the chat. There's been some comments just as you've been, working away there, Greg. Actually, people enjoying the talk halfway through, so it has landed very, very well. You have put out a lot of information in that session. There is a lot. There is a lot to go over. And I'm pleased to see there are some questions coming through. The couple of bits I'll just call out, if you're putting questions into the chat, please could you put them into the Q&A? The reason we ask that, it just gets lost in the chat. If we get a few emojis or people just kind of having other types of conversations, it can get lost. So if you can put it into the Q&A, that would be massively appreciated. The other thing that I'll call out in the Q&A is possible to upvote other people's questions. So if you haven't got a question of your own, but someone else has asked one already that you like the look of, give it a little thumbs up, and we'll use that as we go forward. There was a lot of emojis there. I'm old school though. I do like a comment in the chat. So if you'd like to say thanks, or you particularly enjoyed any particular piece, just give us a little name. It's nice to put a name to the comment, is the other thing I'll say. In terms of that, Greg, if you'd like to open the Q&A feature, we'll be able to work through these. You'll be able to read along as I kind of read them out. Probably what I'd ask, mate, is if you just click on, instead of most recent, if you choose most upvotes, that helps us see whose questions are proving very popular. And just as you're doing that, I will start with a couple of shout outs. So Federico has been into the chat. Thank you, Greg. Really interesting. Thank you, Federico. I appreciate the comment. Kiers, excellent talk, Greg. It was very well explained and so coherently. Thank you for making this topic so engaging. And mate, that definitely came across. The passion and care that you have for the subject came across when you were delivering the session, man. So massive thanks for that.
Thank you. I'm happy you really enjoyed it and you found it very informative. So I'm really happy that it landed.
We love it. We love it. After the session finishes, you'll definitely get a bit of adrenaline. I'm sure of it. You get a bit of a buzz up, bit of a buzz after these things. I will jump into the Q&A. The question that's at the top on my screen is from Adino. It's had 8 upvotes, Adino. So well done. You've clearly asked a good question. Adino's asking, when do you decide to use the graph approach to a data problem versus using classical machine learning?
Yeah, so that's a very good question. So I would say there's many different avenues of answering that question, because that in itself is an art, right? Within machine learning, is to just decide what type of model you're going to be using. It's the eternal question. It's a part of hyperparameter tuning, if you will. But I would say the simplest answer to that would be the type of data and how much data you have. So if you have a lot of data, is when you would start to, again, go into the realm of neural networks. And then it depends on your kind of structure. So you have to look at your relationships themselves. So retail data, for example, lends itself to graphs really well because it's relatively sparsely connected. So that means that not every single customer interacts with every single product, which kind of makes sense because as a customer, when you walk into Tesco, you don't buy every single product and then you walk out, right? That doesn't really make sense. But it also means that you can learn meaningful insights from the interactions themselves. So it's best to ask the question that already on a relationship level, is it going to give me somewhat of some meaningful information, even if I just, without adding, that extrinsic data. Sorry, I think I went out of focus for there. Even without any extrinsic data, can I already start to draw some reasonable conclusions? So just as a human, just have that think beforehand. And for retail data, it makes absolute sense because of the products that you surround yourself with. Already gives you some insight, even without using any machine learning techniques, to kind of start inferring what kind of products you might be interested in as a person, versus as if you all interacted with everything, then the structure itself might not bring that much information. You might still just resort to using regular tabular data.
Amazing,
Yeah.
amazing. That makes lots of sense, and that and actually feeds into the next question there from Stephen. So you may actually have already covered part of it there, but it may be that we can build on it as well. But related to Adino's question, can you give examples where GNNs give performance improvement over classical ML? How big is the improvement? So I guess maybe leaning more on that performance aspect as well. What does that look like?
Okay, so in terms of the performance aspect, so that is obviously a very, very good question to ask. Um, it, I would say at the moment, GNNs are trying to, so there are obviously some case studies within papers where there is a performance boost, but I would say that just by virtue of using GNNs necessarily, you can't always expect a performance boost. Where I believe GNNs kind of break through in terms of kind of like a business setting is by simplifying the overall kind of pipeline. Because for regular ML techniques, you actually spend a lot of your time engineering features, kind of bringing in subject matter experts, and then obviously you engineer all those techniques through a lot of kind of cost and personal time and all of those things. Um, and then you already have a good working model. And I feel like GNNs can match that performance or potentially go beyond. And again, that depends on the data science. It's a very kind of contextual question. But what GNNs truly excel at, in my opinion, at the moment, is if you're going between different business verticals, if you're trying to apply as a business your solution to different problems. So instead of having to bring in again subject matter experts and re-engineer all those features, GNNs try to pick that out for you specifically. So that makes the pipeline so much easier.
Amazing. Thank you, man. I'd found the mute button there, and it always takes longer than you think to get back. So yeah, that makes loads of
Yeah.
sense. Boris, you've put a question in the chat, Boris. Get it in the Q&A, mate. Get it in the Q&A. We'll get to it. Oh, well, we'll do our best. There's a lot of questions, so I'm going to keep them. I'm going to keep them moving. Um, it's actually another question from Adina. I'll try not to do two for the same person, but I think this will be topical actually. So thank you again, Adino, for the question. Adino's talking about data careers. So specifically in terms of data careers working with graph structures, what kind of knowledge or skills or backgrounds are required? Do you need to have a PhD specializing in the area? So I guess in terms of learning these techniques, further reading, further resources, recommendations, what would you say to that one, Greg?
Um, I would say that okay, so I think no, a PhD is not necessary. It helps for a research kind of oriented role because in a PhD you do a lot of research, so it kind of just makes sense that you're kind of used to reading papers and working independently and these sorts of skills, soft skills, or yeah, soft skills kind of come in handy. But I would say it's definitely not necessary to have a PhD. What I would say is definitely a really big interest for the topic and kind of just the kind of curiosity and the ability to kind of read papers and kind of try and implement new models, see where the boundaries are being pushed. And if you maybe are coming from academia and you don't have a lot of industry experience, then working on personal projects, just coming up with certain things that you might be able to apply these papers to, or just out of personal curiosity, the usual kind of things, just to kind of showcase in an interview or perhaps somewhere where that I've been actively working on this out of my own passion. And I think that that just really shows that you have kind of like the aptitude to do this research and the interest in general.
Amazing, great answer. Absolutely love that. The next question, I'm being so rapid with these. I'm conscious of time, and I'm just firing
That's fine.
through. The one I've got at the top now is from Ed Barter. Thanks for a really interesting talk. Ed says the graph representations you talked about were all aggregated over the transaction history. I was just wondering how you handle the temporal elements of the graph descriptions. I'm not going to lie. I quickly had to Google temporal to make sure I was on the right
Yeah,
thing. But we're talking about how data changes
yeah,
over
yeah.
time.
Over time,
Yeah.
exactly. Wow, Ed, you have touched on a
He's in
massive topic.
seasonality. How do you do it? What happens
Seasonality
at
and everything.
Christmas?
So I would say that so right now this is perfectly well pointed out. I've mostly talked about static graphs. So graphs that would have been accumulated and they don't really change over time, or the temporal aspects have been kind of suppressed. So but this opens a whole Pandora's box of things because kind of putting temporality or time-based, I suppose, features or just understanding of the time-based evolution of graphs is a really massive research topic within graphs right now, because you can do it very simply and just do some sort of positional encoding that you might use in transformers, or you might do some sort of again, temporal encoding, and that's very nice, and it does work. So I've worked on models that use that, but it's very superficial, and it doesn't really feel nice because it's not really graph native way, you're just bringing it in from the outside. So the real research kind of topic right now that is really also hot is to do it in a graph native way, such that it just makes sense instead of just bringing in and kind of shoveling it in from the outside. Yeah, I think you might be muted, David.
You just had me saying how much I love that answer. So yeah, perfect. But well spotted, well spotted. Keeping it going, Alex. Thank you for the question, Alex. What is your preferred tool chain for working with GNNs?
So I assume by toolchain you mean like kind of libraries, right?
Yeah,
Uh,
potentially, or like
but
stack
yeah,
potentially.
stack, right?
Yeah.
Um, okay, so I so just like with neural networks, we tend to work on, well, we aim to work on GPUs because it does speed up our kind of processing a lot, especially when you're working with a lot of data. So we work with a lot of NVIDIA GPUs at dunnhumby. So, and we're using a lot of GPU heavy libraries. So of course, I I tend to work with PyTorch. Just it's kind of just closer to me. I find the syntax a little bit closer to my heart, but obviously you can do everything I said with TensorFlow as well. So there's no bias, only in me. um, so yeah, so there's a lot of GPU based TensorFlow. So PyTorch got mixed up a little bit. But I also use a lot of NVIDIA libraries as well. So for example, QGraph or QDF. So they're basically just GPU-based kind of optimized libraries that you might be using on NVIDIA GPUs. So these kinds of things.
Fantastic, fantastic. I love the way it's
Mm.
just, oh, just using a few
Yeah,
GPUs, just
yeah,
something I've got access
yeah.
to. Yeah,
Same.
perfect.
Also, a lot of the architectures, I have used some open source architectures to kind of experiment around with, but most of them, because again, this is a kind of like an active area of research, are kind of custom coded.
Yeah.
So I'd be using custom kind of setups. Yeah.
Amazing. Thank you, man. I'm going to do two more questions. I'm shooting straight to the bottom. It was a question that was in the chat, and I called Boris out. I was like, put it in the Q&A, and he's done it. So I feel like that deserves a little follow through. It's very specific. I don't know whether it's a side project or it's a new project at work, but Boris is saying, I want to implement a very simple recommendation engine. I have a few thousand products. I have no experience with graphs. What graph database and model would you recommend? So again, the reason I've called this one out, I think perhaps people in the webinar may be wanting to learn this, and it sounds like by having a bit of a case study or a bit of a thing to work on, they can get started. So what would you say to Boris in this instance?
Simple recommendation engine. Okay. Well, of course, I don't really like recommending just specific
Blind.
models because
Yeah.
it could be anything. You might implement the model and it might turn out to be utter rubbish, and it might just work well with just a simple random forest. So it's hard to say. So don't take my word as gospel. But model wise, for just a few thousand products, potentially, let's say, maybe a graph convolution network or something relatively simple, because it is quite a simple setup that you have. So there's no need to kind of go really heavy with the graph networks themselves. Um, yeah, so database wise, I mean, I don't think you need to use a graph database. It seems like you don't have that many products. So I think you could probably just find a way to feed the data in through just some pre-processing setup and potentially, just I would say graph convolution network should work quite nicely. And again, you can engineer some of these new nice features which I was talking about, and maybe that can improve your model.
Love it, man. I love it. What a lovely end as well.